Okay, thanks so much. Thanks to the organisers for this chance to speak to you all. I'm going to be talking about some ongoing joint work with Johannes Kleiner and Toby St. Smith. We're looking at the predictive processing framework of cognition and trying to understand it in terms of category theory to gain some insights into the theory. So for those who haven't met it, I'll just do a quick overview of predictive processing to get started. We just had some nice introductions to it from Maritz and Friston in the other room. So here we're thinking of it as a model of cognition that you can apply both at a very low level, say to like a single neuron, and it's supposed to be something that can also apply at a high level for a simple brain or whole organism. And when I talk about predictive processing here, I'm really talking about what's normally considered a subset of it, this variant called Active Inference, that's developed by Friston and his collaborators. The basic idea is that the system comes with what's called a generative model, which essentially is a model that explains how the observations it's receiving from the world can be explained in terms of some hidden states. And what it's trying to do is make this model as accurate as possible, either by sort of inferring these hidden states, which is called perception, or by acting to change the world to fit its model. So you have both action and perception in this framework. And both of these things are achieved through some kind of Bayesian inference in the setup. And in active inference, this Bayesian inference is done practically by minimizing this quantity called free energy. So we're going to meet all of this again as we go through the talk. The important thing about the framework for us, really, in our approach, is that the way predictive processing works is very compositional in its nature. So you look at these generative models, and they're structured in these diagrams. They have many interacting variables plugged together into things like these hierarchies. And the mathematics of studying these kind of compositional systems is called category theory. So in this approach, what we're doing is we're using category theory to try and give a nice conceptual presentation of predictive processing itself, which will help clarify it, and it also lets you, by changing category, for example, generalize the theory to new settings, and hopefully may be unified with some other stuff, other theories that have been developed. So in particular, this is part of a FGO side project we have about looking at theories of consciousness with category theory. And in some previous work that I talked about that I did with Johannes, which I spoke about in the Oxford conference, we applied the same sort of approach to studying IIT. So the real aim would be to have one kind of framework where we can have predictive processing and IIT treated together. Everything I'm talking about is work in progress, so just bear that in mind. So I'll start with this setup now. The actual language we're going to use is what I call categorical probability theory. So it won't really need to be too formal in a sense, because what this approach really lets you do is reason about probability theory and probabilistic processes just using these nice diagrams called string diagrams. So if we have a process between two systems, A and B, we think of this as some probabilistic map, so basically something that sends elements in A probability distributions over B. You could represent this by a matrix, as you normally would say in equations, but here we're just going to draw it as a box like this. This is a basic example of a string diagram. Sometimes you're going to be talking about channels. These are the ones that are actually kind of normalized, so they really genuinely do send points in A to distributions over B. But we do allow more general processes as well. So what you do with these diagrams is you plug them together. So you have these diagrams for a single process. You can compose them in two different ways. You can either compose them in sequence, and in probabilistic terms, this corresponds basically to summing over this variable b that's in the middle. So that's this composition in the bottom left. Or you can just run them in parallel. That's what's going on in the bottom right. And this is like taking two independent distributions, basically, or two independent processes. And the point of using the diagrams is that it lets you translate the kind of reasoning you normally do with equations in probability theory to something you can just do with these diagrams that are hopefully easier to play around with. So for example, we don't have to write this equation in the bottom left, we can just draw this diagram. And some stuff you'll see as we go that's kind of important are distributions themselves. The distribution over A appears just as a box with one output, y for A. And so this would be what a distribution omega looks like in the setup. Another important thing we can do is copy a system, so that's this dot at the bottom. The diagrams are always read from bottom to top, so this white dot is a process that takes in one copy of A and puts out two copies of A, and it's copying all the elements in there. And we can also marginalize stuff in this framework using this thing that's called discarding. So this symbol, this omega that you see, is that would describe a joint distribution over A and B normally, but what we can do to marginalize it is just to throw away this output for B. And that's the discarding symbol. So formally what we're doing is working on what's called a copy-discard category. And this is a general diagrammatic approach to probability theory. But you don't need to worry about the general case here. We can just imagine you're working in a simple category that is called prob there, which means all these Y's are just finite sets and the maps are just like positive matrices between them. But if you want, you could reinterpret the same diagrams in slightly fancier settings like Gaussian probability theory, or working with full measurable spaces and so on. So predictive processing, what we're looking at a lot of the time, are these generative models. So how do they appear in the framework? Well, they're quite simple to describe. So a generative model, M, is something that explains how some hidden states, S, cause observations, O. And it basically just consists of two types of channel. So one is a distribution called the prior, so that's this box, just an output Y for S. And the other one is a channel, it's often called the likelihood, that's going from S to O. So the prior tells us which states we think are likely, just to begin with, and the likelihood tells us, given a state, what observations would it be likely to lead to. And that's all a generative model is, so you can just draw these two boxes. Often the way you study it in terms of this joint distribution it gives you over the pair. So it tells you which pairs of states and observations are likely to come out together. You could treat that with equations, like you see in the bottom right, or you can just draw this string diagram where you prepare the prior at the bottom, you copy it out to get this S output, and you run through the likelihood channel to get your O output, and it gives you this joint distribution over S and O. It's described by this box. So that's all well and good, and it's nice that we can describe generative models well in the framework. But the kind of models that you get in predictive processing are a lot more structured normally. So they involve many variables and all interacting together. So we need to describe these more complex ones as well. So the standard way to do this would be what's called a Bayesian network. So formally this would be given by a directed acyclic graph, along with some kind of probability distribution that's compatible for it. This is an example of a Bayesian network from a predictive processing paper. So we want to know how these things are represented in the formalism. Luckily, there's this known result that says they correspond very nicely to certain types of string diagrams, so we'll have no problem representing Bayesian networks. So the result is essentially from this paper by Bart Jacobs and his collaborators, and I've also been thinking about recently with Robin Lorenz, one of the organizers of the conference, in the context of causal models, is the following thing. It says that, okay, you can specify a Bayesian network, which would be a DAG along with its distribution. Alternatively, these DAGs correspond to certain types of string diagrams, and so giving a Bayesian network is just saying that drawing one of these string diagrams and then interpreting all the boxes in your diagram as actual probability channels. And just for an example of this process, in the bottom left we have a DAG with 4 variables, x1, x2, x3, and x4. And it says that x2 and x3 are observed variables, while x1 and x4 are hidden. So we could draw it like that. The DAG is equivalent to this string diagram on the right. So, for example, x2 is one of the wires, and it's prepared by this channel C. So you can see it has an input for x1 and another one for x4. So those are its parents in the DAG, so they become inputs to this mechanism C that produces it. And x2 becomes an output for the diagram that gets copied out there. And similarly for x3, whereas x1 and x4 are hidden so they don't end up as outputs. So why would you choose one of these representations over the other? The advantage really of working with a string diagram is that, as I mentioned earlier, you can do kind of probabilistic reasoning just with diagrams. So if we work with the string diagram approach, we don't need to carry around this DAG plus a load of probability theory with equations and so on. We can just work with a single entity, which is the diagrams themselves. So we can use this now to describe the kind of generative models that you get in predictive processing. And basically, in the kind of discrete time case, they end up all looking something like this, or at least the simple ones do. So I'll walk through this one. So this is a model of how you have a system evolving over n discrete time steps. So there's a hidden state space, S at each time, so it's S1, S2, and so on. Remember the diagram's going bottom to top. So each state S at a given time will lead to some observations, so that's called O1, O2, or so on. So that's produced by this channel A. And then the diagram, or the model is saying, okay, well, the state is evolving based on the previous time step, and this extra thing called P, which I haven't described yet. And that's why these channels P. You can see S1, S2 as you go up the diagram as time moves on. And this P stands for policy, and these are the ways that action into the picture in predictive processing. So policy is also called an action policy. It's basically a type of behavior, so it's a sort of a choice of action at each time step, if you like. So the model says, if I'm going to act in this way, and this is this current state, then these are the likely states of the next time, and so on. And finally, at the bottom, we have a prior to these policies, which you can think of as the habits, the habitual behaviors of the system. So this kind of diagram basically describes a discrete time model, which come up all the time in predictive processing. The other thing you do with these models is often plug them together into what's called a hierarchical model. And these are quite nice to treat with the diagrams as well. We can literally take several generative models, plug them together as diagrams to build these kind of hierarchical setups. And the idea of in a picture like this would be that you'd have a kind of, actually a high-level variable would be at the bottom of the diagram, because of the way we read these diagrams. So this thing coming in at the bottom would be something like, the space describes different objects, whereas at the top you're describing different individual pixels or something like that. Or it could be time evolving, where there's sort of slower time scale features evolving at the bottom of the hierarchy and quicker ones at the top. So far I've just said that basically generative models are nicely described in this framework. Now we want to see what you actually do with them in predictive processing, which is normally about inference. So we want to know how inference can be treated in this approach. So let's say we have one of these models with some states and observations, and now we actually receive an observation. So everything's done with probability distribution, so this is now one of these boxes describing a probability distribution called O here, which has one output. So this is like a new piece of evidence. So we want to say which states likely cause this observation. So this is the process of updating our model. We already had our prior, which told us our beliefs about which states were likely, but now we know more, and so it's probably going to change. So this new inferred distribution is this M given O, this box on the right. And this comes up all the time in predictive processing. It comes up in perception, where the state is like the hidden explanation for your observation. And it also comes up when you're choosing how to act, in which case S would be replaced by the policies. And so you'd be inferring what policy to act to obtain some given outcome. So we want to know how we do these inference in the framework. And the standard answer is with something called Bayesian inversion, but when this observation is soft, so it's given by an actual distribution, so it's not just one precise point, but it's a distribution over O. There's actually two different ways to do this inference. And I don't know if it's been explored that much, so I thought I'd mention them here. The first of these is that you construct this channel. So normally you have one from S to O, which tells you how states cause observations. And you can construct the Bayesian inverse. So that's this box M dagger that appears in the picture there. So that's going from O to S instead, and you just plug the observation into that. So this is one way of doing this update procedure. And so the result distribution, the whole diagram is described something of one Y over S, so it's a distribution of S, and that's a new posterior distribution. There's a second way to do it, which here are called conditioning. So the two methods have been explored by Jacobs in this paper cited at the bottom, where he kind of compares them in more detail. Roughly, with this one, what you do is you plug the observation into a model and then just normalize everything. So these two approaches, the dashed box indicates normalization. So the difference is roughly whether you normalize with respect to the observation or you kind of normalize it in advance and then plug it in. But I'd really like to understand more how each of these relate to normal kind of approximation schemes that you do in coding, which one's more natural there. They're not normally distinguished because if you plug in a sharp observation, so just a point in this observation space O, they'll end up coinciding, so they're not different there. Whichever one you pick though, the problem is that they're quite hard to compute. They involve summing over this whole space S or O. And so you don't calculate them directly. What you do instead is approximately carry out these update procedures by minimizing a quantity known as free energy. So I don't think I'll have time to say too much about free energy, but it's probably good to know that it is at least fitting in our approach. So we can define this general free energy kind of functional, which takes two generative models, S and O, and roughly it just tells you kind of how surprising one model is relative to the other. Normally you'd write free energy in terms of some expectation values, but here we don't need to write the equations out, and expectation values is basically plugging two boxes together. So this formula is essentially the same as what you'll find in the free energy literature. Specifically, the way you use it is to do this approximate inference stuff using what's called variational free energy. So before I was talking about how we want to do this update to get this distribution over our states, but we can't do that exactly. So what we do instead is we do an approximate one. That's what this box Q is. This would be your approximate distribution over S. And you get the best one by minimizing this quantity called variational free energy. And all that matters in the diagram really is that we're kind of measuring the difference between this pair consisting of Q and our observation O, and seeing like how surprising that is relative to our model M. So if you minimize this quantity, you can show that in fact you'll end up with a Q that approximates this Bayesian inverse. There's a second way that it's used in predictive processing as well. That's another quantity won't be too important to go into details of this one though, but it's called expected free energy. And the point is just used when you're choosing how you want to act based on some future preferences. So in this box, C would be a state describing your preferences about future outcomes. And to get the ones, to calculate how likely they are, you can calculate this approximate quantity called the expected free energy. So we've kind of gone through the ingredients of predictive processing formally. We've got models, inference, and this free energy stuff. And now I kind of want to put it together to talk about active inference itself and what this looks like in the approach. And the nice thing with the diagrams is that you can reason about it in quite a high-level way. So very roughly, active inference is something you can think about when you've got a model, any kind of model that takes this form we see here. So it's basically like this discrete time model I showed earlier, but now there's only 2 time steps. And really, these could have more structure, so each time could be like the first 1,000 time steps, and the next one is the next 100,000 time steps, or something like that. But we can just take a higher level view and just think of it as 2 times. There's the current time and the future time. So we have S would be current state now, and we receive this observation O. So we receive some new data from this observation. And we have a model saying that, okay, the current state is going to evolve into this future state, S dash. I have some preferences about what observations we want to get in the future, F. And at the bottom, we see how this is being controlled by our action by these policies and our prior over policies, E. So we have a model that basically is about current states, observations, and future states, observations, and our actions and how they change those. So what active inference is applying this inference setup I talked about earlier to choose what your policy should be. So you're given an observation, O, which would just be a box like this, and I'll set this box to O. And you have some preferences, which are called C here, which are about what you want to happen in the future, F. You've got that, and now you want to do inference. It's basically like the kind of inference I talked about earlier, but now we've got these 2 boxes, so it's a slightly more complicated problem. And when you do inference, you call the thing you do at the end your plan, because it's a distribution over the policies, and it's describing, which types of behaviors you think are the ones you want to go with. So in a way, what you're kind of doing is answering a question like, given that I've got this observation, and that I'm going to get what I want in the future, but you just assume you're going to get it, then you're saying, what policy am I in fact pursuing to explain these things? If you read through all the literature on active inference, they give you a kind of formula for how you should do this. So they say it will be justified in terms of the free energy principle in various ways, but there's some formula that's given in terms of your habits, and these quantities of the variation on the expected free energy that I mentioned earlier. But it can be, I think, a bit mysterious to work out where this expression exactly comes from. It's been derived in a few ways, but it's normally in terms of the expected free energy being some kind of prior, and you're doing inference with that. What I'd like to see instead is just some way where you just apply this machinery to the structure of the model that we had on the last slide, and this formula will just come out for you for free, so it's quite generic, quite conceptually justified. So I'll try and quickly show that at the end. We'll probably have to go through it quite quickly. But very roughly, what we want to do then is build this plan. It's a distribution over our policies. And we're going to do it using this inference method I talked about earlier. So we just simply, I'm using the one called conditioning. We've just got our model, M. It tells us how policies relate to these observations and these future outcomes. And we're just going to plug in what we've got, which is our observation O and our preferences. And then we normalize the whole thing. And that will be our plan for how to act. So we want the diagrams to kind of help us break this down into eventually getting to that formula that we had. So let's just look at this picture here. To begin with, we know a bit more about our model. We know that it has something to do with these current states S. So I'm just going to break the model up a little bit like that, and draw it like this. So we have our habits at the bottom, we have our current state and observation in the middle, and we have the future stuff at the top. And what you do in active inference is you start by looking at this part that relates to the current time. So you have this box that's saying for each policy, what's the likelihood we're going to get that observation for each state. And you approximate this using the variational free energy stuff I mentioned before. And that whole process can be called perception. So when you're doing inference over states, that's often called perception. So very roughly, we can think of perception as a channel like this that takes the observation in and a policy, and it produces this distribution over S. The key point is just that there's a nice way to rewrite the diagram in terms of this approximate approach of using variation free energy. So now we have this box for the free energy, and you have this Q, which is your approximation for each policy. So it's your inference about what state is probably the cause of the observation. Okay, then fine, what we can do is plug this in at the top, just rewrite it, call that composition MQ. So now we have a model for each policy of what we think are the likely outcomes in future, and we now want to approximate what's in that blue box now, and this is what you do with the expected free energy. I don't think I have time to say much more than just to say that's what you do, but it's there's an approximation to the surprise, which is essentially what this box here tells you for each policy. So we've rewritten the string diagram to involve this free energy quantity and this expected free energy quantity, along with habits. And if you remember, what we're trying to do is normalize that whole thing, and if you do that, because there's exponentials in there and so on, you get this precise formula that we saw earlier. So it comes to softmax, and you have a term for your habits, and a term for each of these types of free energy. So the point of that was just to give a bit of a flavor for how the diagrammatic reasoning works and can be applied in predictive processing, and also to try and see where this expression comes from in quite a direct way, where we just take a high-level view of the model and apply the inference machinery to derive it. So just to wrap up, I've just tried to explain how you can use this framework, this diagrammatic virtual probability theory, to capture the main ingredients of predictive processing, generative models, this inference, and then active inference itself. There's obviously way more to think about, but I didn't say anything about how this Q, this approximation for each state, is actually calculated. That's done normally with these schemes called message passing, so we want to think about those categorically as well. Again, I think there's more to think about in terms of these two inference methods I mentioned. I don't really know in which one should be the preferred one in terms of active inference. We used conditioning for the derivation there, but the other one might be, favored in some way. And finally, I didn't have any time to really directly go about the connection with consciousness, predictive processing. That's obviously what we're going to look at next. So there's been all sorts of proposals for how consciousness relates to these generative models and so on. And we want to see them manifest in the framework. And the point of it was to use the same framework that we used to study IIT before, and that we think can also be applied to global workspace theory. So at least we can have all these theories sat alongside each other within this one categorical framework, and then talk about applying them to the same kind of systems and maybe comparing them. And that would be quite exciting goal for future work, I think. But that's it for me now. Thank you.